In this video, I'll go over how to use a PulseBlaster and an NI DAQ card with Labscript. As of early 2021, PulseBlaster and NI DAQ cards are two of the most commonly used devices with the Labscript suite. And you'll see why, because between the two, you have the ability to clock your experiments, provide digital outputs, and also analog inputs and outputs. To run these devices, we'll need APIs that interact with the devices and with Labscript, and act as a go-between. For the PulseBlaster, that is the Spin API. Spin comes from the Spin Core company that makes the PulseBlaster, and they provide this API that has Python functionality, which you can download and install. The other is NI DAQ MX. This is for NI DAQ cards, and this is provided by National Instruments, again, for interacting with your Python software and your device as a go-between. So to get going, we have to make sure these are installed. So we will do this within command line, command prompt, and an Anaconda environment. So in the last video, we set up Labscript within an Anaconda environment, and I called that activate environment. I called that environment Pi38. So we'll, from an Anaconda prompt, we'll run activate Pi38. And then I believe you can use pip to check to see if Spin API is installed. Okay, so it's installed, is probably installed with Labscript. And then we can similarly do that for NI DAQ MX, which I believe is just called NI DAQ MX. And that's also installed. So we're good to go here. Yeah, so now we could just go ahead and open up Labscript and get going. Of course, if you didn't have these installed for whatever reason, this would hopefully just take you through the process of installing them. So to run Labscript, I'm going to open up Blax. Remember, Blax is the application that actually interacts with all the devices in your experiment. It takes in compiled scripts and runs them in a sequential order to run your experiment. And it also just allows you manual control of all of your devices. Right now, we only have these two devices that are set up. This is just very general intermediate device, which means nothing, and pseudo clock, which also basically means nothing here. So these are not real devices, and by the end of this video, hopefully we will have some real devices installed, namely a PulseBlaster and an NI DAQ card. What devices show up here and what you're configured to work with is determined by the connection table. So that's a file that you must edit. If you've set your config file to use something you have right now, you can click edit right here within Blax, and it should prompt your text editor to open the connection table. In my case, I configured this to be Notepad++. You can find this in Labscript, users, Labscript config. In this case, it's this file right here, I believe. And you can see I've set this to be Notepad++. If you want to use something else, you can set that to be something else. Okay, so the other way you can access the connection table, if it didn't automatically do that, is from within Labscript. So go to your C drive. Hopefully this is where your Labscript installation put it. SS Lab, this is my username. Labscript suite, here's a Labscript suite. And then connection tables should be generally stored where the experiment files are stored that they go with. So in this case, it's userlib, Labscript lib. So this refers to experiments that are used for running, Labscript files that are used for running experiments written by the user. And then, for example, example apparatus, which I think is what's set up right now, but of course it's easy to change this to other things. So here you can see the connection table, and this is actually the connection table that was automatically opened when I tried to edit it from Blax. Okay, so if I wanted to see other devices here, I would need to change them here. You can see that they're declared here So I can see I have this intermediate device. That's this thing right here. You can see the name intermediate device. If I were to change this name to be something else, like int dev, I'm just making something up here, and I wanted to call it that, I could. And what I could do is I could save this and compile it, and then it should change it over here. So if I hit Control S to save it. Oh, also, actually, excuse me, I put that in the wrong spot. This is right here where it says dummy intermediate device. This is where it's declared, the name is given. And then this analog out is saying that that is the device that it's supposed to be associated with. So you have to change it here where it's named, and then in my case, there's this analog out that also needed to be modified as well. It could be any number of these analog outs depending on your device and what you wrote in here. So now you can see that as soon as I modified this and saved it, Blacks recognized that and gave me a warning that I need to recompile the connection table. And that's because the connection table that I'm modifying here is a Python file, it's .py, but the thing that's actually read in, I think, is an H5, an HDF5 file. So the compilation here will convert it to an HDF5 file, which is read in. So I'm going to recompile. Okay, so I made a mistake. That's because this is also named that. Okay, so it's good that it tells you that. So I'll Control S again to save, and I'll try it again, compile. Okay, this is just a warning about version control. You can ignore it. Mercurial is a version control program. Anyway, compilation succeeded, restart when ready, so you have to then restart Blacks. And now you can see the name has changed. And that's just from modifying the connection table. So, so this is how these two things are connected. And you can see that if we want to get a PulseBlaster working, we'll have to modify this connection table. Okay, so let's go ahead and do that right now to make it work with the PulseBlaster. Basically, the PulseBlaster is going to take the place of this pseudo clock. So the first thing that we're going to do, I'm just going to get rid of this. We're going to call this digital device, perhaps. And in my case, my PulseBlaster is a PulseBlaster USB. If I go and look in Labscript and I go to Labscript devices, again, this is in the developer mode. You won't see this in the regular installation. That's what you installed. You'll have to reinstall or switch to the developer installation to see all of these options here, Labscript devices. Okay, so if I go to Labscript devices, then I can see some of the already written scripts, servers for different types of PulseBlasters. There's a variety here, and the one I'm going to use is this PulseBlaster USB. And within PulseBlaster USB, I can open this up, and you can see that there's a class called PulseBlaster USB, which creates a PulseBlaster USB object. And so that's the name of the thing I'm going to use here, PulseBlaster with a capital B, USB. And so this is declaring a new object of this type. And then I need to give it a name. So I'll just call this something very mundane, PulseBlaster. Maybe I'll give it a 0 just to specify in case I have new ones in the future. There are a few different options that you can add in here after the name. I think one way to get to what they are is notice that PulseBlaster USB inherits actually from something called PulseBlaster No DDS, stands for No Direct Digital Synthesizer. And so that is PulseBlaster No DDS. There's all these classes that are imported, inherited. So we can go ahead and look in PulseBlaster No DDS to give us some guidance on the options, the arguments, the optional arguments. And if I look in here, I see that under init, okay, so the init doesn't actually give me a lot of guidance here. So maybe I'll look to see what this inherits from. This inherits from PulseBlaster. So let's go ahead and look at PulseBlaster. That's PineBlaster. PulseBlaster. Okay. So in here, okay, so here's the init function, and you can see there's the name, and then there are all these optional arguments one can use. I think a pretty common one to include is the board number, and programming scheme, because this actually does sometimes change depending on what you're doing, although we probably won't cover that, and you'll want to start with PB start branch to get going. Let's see, I think that's it. I think that's all that we usually, those are the only optional arguments that we normally want to declare here. So now we have a device, a digital device called the PulseBlaster USB, which we can refer to later by this name, PulseBlaster 0. Now we're going to declare that this PulseBlaster USB device is the clock line. So I'm going to define the clock line, and it's called clock line. This is, I could look inside of Labscript.py to see this, but you can see that these are some different types of device classes that one can use. Clock line is one of them. That's what we want to call it, clock line. And so I'm going to use, let's see, I guess I'm just going to call this PulseBlaster 0 again, but I'm going to call it maybe clock line. So this is kind of, in a meta sense, a separate device, but it's really kind of the same device. It's really going to be specifically one channel from the PulseBlaster. If you have another device that produces digital outputs, I believe you can just use that instead. Of course, you'd have to declare them up here, and then just define what channel is going to act as the clock for your experiment. Let's see. Okay, I'm looking at my notes here, and I guess I'm not actually sure that I understand this part here, but for some reason, the pseudo clock, maybe someone can comment on this. There's this option here that needs to be specified, or may need to be specified. I can't confirm that. And then, but importantly, connection flag 0. So this is defining. So on the PulseBlaster itself, we would then use the channel 0, which is the first channel. It starts from 0, counting from 0, as our clock line for clocking other devices. The PulseBlaster itself will be sort of implicitly clocked by itself, which is convenient. Okay, great. So now we have a digital device and we have a clock line. And we can stop there for now. We can get to the NI DAQ card later. Let me see here. So I think for it's not clear to me whether or not I need to. Yes, I think I need to actually define. I may need to define the clock here for this intermediate device as this, now that we've changed it. Yeah, I think that's correct. So now this dummy intermediate device is going to be clocked by the clock line, which is the PulseBlaster USB. And I guess we'll see if that actually works, because this is not a real device, it's a dummy intermediate device. I haven't actually tried that. What we might actually do is we might just remove this for now. We don't really care about it. So I'm just going to remove both of these things, and we'll just have the simplest of all possible setups, where we just have a PulseBlaster and a clock line at the moment. Okay, so I'm going to hit Control S. You can see that this has already told me. I guess I must have hit Control S earlier. Oh, one more thing. I forgot to actually import PulseBlaster USB. So I'm looking up here and I'm seeing that I've got the wrong thing imported. I don't really actually care about either of these right now. But what I do want to do is import from Labscript devices PulseBlaster USB, import PulseBlaster USB. So what this says is go look in Labscript devices / PulseBlaster USB. Okay, so that's here. And then from within this file, import the class PulseBlaster USB, which will then import all the other things that we need. So great. So hopefully this will work. I'm going to hit recompile. That's because I probably need to import clockline. Let's see if that helps. Okay, let's just try instead importing everything from Labscript. Maybe not the most elegant solution here. Oh, maybe it's that actually clockline it has a capital L. That would make sense. That's a camel case for you. Great. Okay. There's one missing positional argument in okay. Let's just see if this works without this. Nope, I guess I do need that. I must have, okay, what did I do? Pseudo clock arguments. Let's try, oh, maybe this is calling, oh, did I just spell it wrong? I bet I spelled it wrong. Oh, I've got my E's and my U's backwards. Okay, I think this makes sense. And it succeeded. Great, so you do need this. That's an important argument. Okay. Okay, great. So now it's compiled, so let's restart Blacks. Okay, lo and behold, we have a new device here. Although it's not starting. And that could just be related to, oh, it may actually be that I may actually need to download Spin API onto this computer, even if it's set up in Python. Yeah, that could be true. Okay, let's try just going to Spin API again. Latest Spin API, right, universal installer. Okay. Pretty sure that's actually true. Okay, let's see here. It's downloaded. I'm not sure if I need to run a installation wizard. Yep. Sounds good. Let's install it all. Yes, so make sure you install 32-bit runtime support because we're on a 64-bit Windows. Yes. Yes. Okay, finish. Okay, this was almost certainly the problem. I'm going to turn off my PulseBlaster and turn it back on again because who knows if that is required here. I'm going to go ahead and close this, and I might just close Blacks and open it again. Okay, I'm just going to restart the computer, see if that fixes it. Okay, so I, in fact, needed to restart the computer to get it to recognize Spin API. And as you'll see, when I open up Blacks, now the PulseBlaster is recognized and loads correctly. Looks like it's communicating correctly. The status looks good. I haven't defined any specific outputs aside from a clock line, so there's really nothing to do here at the moment. But this is great. It's great to see this working. So we can even try running a shot in Run Manager. So here I'm using this very simple Labscript script that I've written. Which I'll just open. I guess I can open it from right here. Let's see. Great. First, PulseBlaster just defines the PulseBlaster and a clock line, and then it just waits for 1 second. And again, the connection table is identical. The front matter here is the same in both cases. Okay, so this should work. I'll just go ahead and hit engage. It submitted the run, and I think it ran it. Yep, 1 second. Okay, great. So that worked. It ran completely, and it was fine. So now you might say, how could we add some actual defined digital outputs here? And that's a great question. So we'll go ahead and do that first. So I'm just going to add a line. Oh, actually, you know what? I should really be doing this in the connection table first. I mean, it doesn't really matter. Sometimes people prefer to do it in their Labscript code first, and then copy to the connection table. Okay, so digital out, I believe, is the name of the class or the object of what we're trying to create here. And we just have to give it a name. So I'll just give it something stupid like digi out 1. How about 0? 1. Let's do 1, because 0 is the clock line. And then I need to tell it what the device is. So the device is this PulseBlaster. That's the second argument. But I need to be a little bit more specific. It's not the pseudo clock part of it. It's not the clock aspect of the PulseBlaster. It's the direct output aspect of it. And if you're confused by this, you could go ahead and look in the code for probably for the PulseBlaster or for maybe for digital outs, and it'll say more about this. But yep. So this is what we need here. And then we just need to specify, I think, what channel, which is specified by the keyword flag, which flag 0 is the clock line, so I'll make this flag 1. Okay, so now I have this digital output. I believe that this will work, so I'm going to go ahead and save this. Remember, this is just the connection table. We'll make sure that this compiles. It does, that's great. We'll restart Blacks. And then we need to copy the connection table, at least the top half of it, into the experiment that we wish to run. now that it's been modified. Okay, so that looks good. And now, if we want to, we can do things with this digital output that we created. You can see actually the digital out now appears in black. So in principle, I can turn it on and off. And if I were to look at it on an oscilloscope, I would see that this channel turns on and off. But I can also do it in an automated way. So here, this program, this experiment that I wrote is very simple. It just starts and then it increments time by 1 second and then it stops. But let's say after that 1 second, I wanted to take my digital out, which is called DigiOut1. Again, this could have any name you want, but I called it DigiOut1, and I wanted to make it go high. And I believe this is you can look this up actually in the Labscript file for it, but I believe this is what it's called go high at time t. And then maybe I want this to stay high for half a second, and then go low again. And that's how you do that. And some people think it's a good idea to define the state of all of your digital outs and analog outs at the beginning, right after start, so you can do that as well. So I'm going to say it starts low, goes high, it goes low again. This would be like a half-second pulse, effectively. Okay, so I've saved this now. I've Control-S. I don't have to change the connection table. The connection table is only this front matter. It's only dealing with the devices, not with the experiment itself. So now I've changed first PulseBlaster.py to run this new experiment. I don't actually need to close and open Run Manager. I can just run it now. It should just work. Maybe I'll turn off Run Shot for a second and just compile it and see if it compiles. It does. I can see that because it says ready to go, no errors. So then I can click Run Shot and it should run it. And I'm not looking at it on the oscilloscope. Maybe I'll do that later. But yeah, it successfully completed. It looks like it ran, so that's great. Okay, so that's cool. And if I wanted to, I can make more digital outs. I could make a second one if I wished. Call it digital out 2. Specify that it's channel 2 on the PulseBlaster. And then maybe I'll start that one low as well. But then maybe I'll have that go high. This is kind of one of the cool things you could do with Labscript if you want to. Is you could even just say like, oh, I want this one to go high. It'd be a little bit of a strange thing to do, but you can say I want this to go high basically at the same time as the first one, but maybe like a 1/10 of a second later. And then of course you have to be a little bit careful because if you get overlapping times and things, you can screw yourself up here. But I'll just do something like this. And now it looks like this pulse will be just start a little bit later, and it will end at the same time. Yeah, and I can save that and run it. I just made a small modification. Run that. Oh, it looks like I did make a mistake here. What mistake did I make here? Oh, I know what. I modified it and added an extra digital output, but I didn't change the connection table. That was clumsy of me. You can actually see here. It gives a little bit of advice here. Maybe the connection table hasn't been set up here. So let me just copy the front matter. As long as it matches the connection table, you're good to go. Okay. Now I've changed the connection table. I have to recompile. Okay, restart. Everything's good. So let's try this again. And now it works. It's great. Okay, so I think that'll conclude getting the PulseBlaster going for now. And we'll move on to the NI DAQ card. So for the NI DAQ card, my NI DAQ card is 6363. It's a USB 6363. And just kind of like we needed to look up what the class for the PulseBlaster was, we have to do a similar thing for the NI DAQ card. So I'll go to, I'll go to Labscript, go there the long way, users, my username, Labscript suite, and I'll look in Labscript devices. Now again, this is because I have these folders available to me because I installed the developer version. If you have the regular installation installed, you won't see these, and you can't actually make these modifications without the developer installation. Although if you don't need to modify anything, you actually can get away with this. You just need to look up the list of the devices that are currently supported in Labscript at the time that you install it. So, but I've installed the developer installation, so that's what we're seeing here. So I can go to the Labscript devices. I can look in here, and I can actually see a 6363 down here. Although it's not the USB, it's the PCIe. Just to open that, look at that real quick. Okay, it says that it's depreciated actually. So interestingly, okay, so actually it will point to the right spot, but that's not really the one I want. It looks like the organizational method right now is that everything, all these NI DAQ MX programs are in this folder. So I'm going to go here, and then I'm going to look in models. Okay, so here's a list of what looks like to be the currently supported NI DAQ cards. Now, there is this nuance that mine is a USB, not a PCIe, which stands for PCI Express, which is a type of connection. This is a card that goes in your computer usually, not a USB connected device. But here's a little secret: it'll still work, actually. But someone, probably me, should probably write a USB version of this specific class. So this is the thing that I actually I need to import. So I'm going to import this up here at the top in. Oh, let me do this in the connection table. So in the connection table, import from Labscript devices. Let's look at the file path here. Labscript devices dot NI DAQ MX dot models, and then I'm going to go ahead and just try this NI PCIe 6363. So I'm going to import that. Gives me the option to declare an object. I'm going to go ahead and create that object right here. Call it an analog device. Which is how I'm going to comment this. And then actually I call calling from this this class here. So it's actually, I believe it's probably just that I wish to. That's the name of the object that I want to declare. I want to create an object of that type, as we say. So there, this is the declaration for that. And so this analog device has a slightly different shape to this digital device declaration. So I'll show you what that looks like. We'll go ahead and just use a tab format here. So first of all, we give it a name. Let's actually give it two names, but you'll see that in a second. So NI, let's call it NI1. Could be a lot of things, really, I think. We'll see if this works. Next thing is I need to tell it what is going to control it, the parent device. And so it's basically what is going to clock it. And the thing that's going to clock it is this clock line up here. Okay. Then I need a clock terminal. So this is the device, this is the port, the connector, the channel that's on the device, on the NI device, that the coax cable that's running from the PulseBlaster is going to be connected to clock this thing. And basically tell it when to run. So in the case here, the syntax is going to be / the name you gave it, and then the name of the channel, which you can look on your device. You should probably look up for your device what a good clock channel would be. I'm going to use a channel called PFI 0. And if I look at my device, it says that right below the channel I'm using. That's where I've got my coax plugged in. And so that's where the clock signal is going to. And so this tells the NI DAQ card to look there for its clock. So we've got this max name. I'm using a different max name than is in my notes here. So I'm actually trying a little bit of an experiment here. I'm pretty sure this will work. I don't know if I have to go into NI max and initialize this with a different name, or if I can just define it here. I hope that this is what I can do. If not, I may need to go in and modify this. The default in my node is dev1, so we'll see. It may actually be that, that's interesting actually. It may actually be that I do have to call it whatever it's defined in max. I may have to set it in max. Okay, so we'll just try this, and then if it returns an error, then I'll show you what to do. Stop order -1. Actually, not sure what that means. It might just mean go ahead and run all the time. Okay, acquisition. So post in the comments if you know what that means exactly, the stop order. It probably says in the code if I go look at it. So for acquisition rate, this is basically going to be whatever you want it to be that's less than or equal to the sample rate of your device. And it's not just the sample rate that's quoted in the spec sheet for your device, but it's also going to have to change sometimes if you use too many channels. If you use more channels, You may actually have to make this, you may have to reduce this. It may have to be some sort of like integer divisor of the number of channels you use. But for this device, it should be 1 megasample per second, and I'll just go ahead and set it to be that. But I could make it, 1 kilosample per second if I wanted to, or I could make it, half a megasample per second if I wanted to. But I'll try with, I don't know how I did that. I'll try 1 e to the 6, that's 1 megasample per second. And I think that's probably all I'll start with in terms of the arguments. Okay, so there's my declaration for my analog device, and I'm going to go ahead and just add an analog output right away. So this is similar, it's analogous to digital out. Call it ANA out 0. The device is this, and we will see if I have to change that name or not. And then I just have to specify what channel. So this is an analog out. This is the syntax we use, AO0, all lowercase. And yeah, maybe we'll just go ahead and try this and see if it works. So I'm going to just copy, this is the connection table. I have to copy this into my experiment file. And I also have to recompile, so let's go ahead and recompile this. This is the connection table. Okay, so look here. So this actually says that the NI63 has to have an even number of analog outputs. I only declared 1 analog output, but you have to have an even number. So that's easy to fix. It's kind of a silly design feature, but I'll just make a second one. I'll call it, oh, I gave this a silly name. Analog, let's call it analog 0 for the first one. Analog out 0, ANA out 0, ANA out 1. Okay, so now I've got, now I've got 2 analog outputs in my connection table. Let's try recompiling. Okay, that worked. So let's restart Blacks and see if it successfully connects to the NI DAQ card. No, it didn't. Why is that? Okay, so yeah, it didn't like this name. I suspected that. I think that the device name is probably actually dev1, but I'm curious. I think, oh, so there's also something else that I did offline that I didn't show here, which is that I installed NI DAQ MX. You will definitely have to do this, and this is exactly analogous to the Spin API problem I had before, where I had to install Spin API and restart the computer. So remember, NI DAQ MX, I have to actually download this. So if you haven't done this, you have to do this. From the National Instruments website, you have to go here, click download. It'll download, and then go ahead and in your downloads folder. Here it is right here. And you have to run this, and this will run an installation wizard, which takes a while to install. And it gives you a lot of options, just accept all of them. And then restart the system. Make sure that you accept, there's I think an option in there for making sure that this will run on a 64-bit system, or maybe not, maybe that was for the Spin API. Anyway, so make sure that you've run this NI DAQ MX installation and then restart your whole computer. If you don't do that, you'll get a different error here where it doesn't even recognize this. But that's installed on this computer. I didn't show that. But now I have an issue where I think I've given this the wrong name. So if you've installed NI DAQ MX, you'll see that, yeah, there's these NI National Instruments programs here, including NI Max. So if I scroll down, I see NI Max. So NI Max is a built-in application that allows you to look at all of your National Instruments devices that are connected to your computer, make sure they're running properly. It has some minimal code for running them. And so this is actually pretty nice because it allows you to check your devices without having to use Labscript. So I'm going to go ahead and go to Devices and Interfaces once this loads. Yes, and as you can see here, I gave it the wrong name, Dev1, but I can give it a different name, I believe. So I'm going to go ahead and do that. I'm going to call it what I want to call it, which is NI1. And let's see, maybe save. Sure. That looks good. Okay, hopefully I don't have to restart it or anything. So now I've done that, let's just try closing blacks and opening it up again. And let's see if it recognizes this NI1. And it does. Great. Good. Okay, so now it actually shows my NI DAQ card. 6363 has 4 analog outputs, and it has some analog inputs, and then it has all these sort of funky digital outputs that are not coax connected. They're just like something else. So great. So now if I wanted to, I could copy the connection table into first PulseBlaster. And actually, I should probably rename this because now it's also, it's got the NI DAQ card. But I'm not going to, I think this is fine. I'll just keep using the same one. And now if you want to, we can define what the analog outputs do. So I'll just set the analog outputs at t equals 0. Oh yes, so now we need to know how this syntax works for defining the state of analog outputs. And believe one way to do this is to use the constant function. So if we go and look inside of, I think, intermediate device, or maybe it's probably analog out. If we look in analog out, that function is defined somewhere, and it'll give a list of methods, of functions that you can use, including, I think there's maybe one called ramp, if you want to ramp an analog output. But if you just want to set it to some constant value, like I would like to do right now, I'll just use this method, which is inherited here, .constant, and I'll just set it to be at the time t at some value, which I'll just say, let's let that be 0. And let's do the same thing for the second analog output. Oops. Which I think I called analog 1. You see right there. Okay, so now this is t equals 0. This is going to set this these both to be 0. I mean, I could also set this to be like, I don't know, 2 volts maybe. Oops, why not, right? 2 volts. And then, at some later time, I could set this one to be, well, let's just set them both to be 1. And then at the end here, I'll set them back to be their original values again. So just a very simple set of commands to happen at different times. And this should change the analog outputs on my system. Actually, I'm going to go ahead and disconnect them from things that they're controlling right now. I don't want them to hurt anything in my actual experiment. Okay, great. So now I've saved this, and I know that I've already recompiled the connection table. I don't need to do that. So I should just be able to run this, and it should run. If I have any doubts, I can uncheck the run, and it'll just compile. It looks like it compiled successfully. So I'll go ahead and run it, and it runs successfully. That's great. Okay. So this effectively shows you how you can get an NI DAQ card and at least the analog outputs for an NI DAQ card and a PulseBlaster working. I suppose I could also show you one way to acquire data using an analog, using an NI DAQ card. So this would be like if you wanted to acquire analog signals on an analog input, if your NI DAQ card supports that. Sure, maybe I'll show you that real quick as well. So to do that, we need to define an analog input. And yeah, I think this might also have to be defined in pairs as well. So the syntax is pretty much identical to before. I'll just call this ANA in 0, NI 1, so I'm telling it with device, and AI 0 in this case. Okay. Oops. And I think I need to define maybe a second one as well. This is this weird quirk. Okay, so now I've changed the connection table again. I'll just recompile and restart blacks. And I'll copy the connection table into the top of first PulseBlaster. I don't need that anymore. First PulseBlaster. Copy this into the top here. Okay, great. Good. So that compiled, and this device is running properly. So the command to acquire is, what is that? Here we go. So what did I call this? I call this NI in. So then, for example, let's say right here, what I do is I say acquire. This is the method one uses. And I have to give the acquisition a name. This is basically the name of where this data is stored, this data set, the data set name, let's say, title of the data set. So I'll just call it my data. It's pretty unoriginal. I have to tell it a start time. I guess I'll just say T, which, yeah, that works. And then this is where it gets a little bit different. I have to define the end time right here. So I don't go down here and tell it to stop. I have to define it right now. And so this requires kind of reading your Labscript file and understanding what's going on. So I don't know, maybe I would want to, let's see, maybe I'd want to just acquire during this 0.5 seconds. So I might just say T plus 0.5 seconds. And so that would work, that should work. So I'll go ahead and save that. And yeah, and now I should be able to run this. And I don't really have a good way to show this to you right now without getting into lies, but maybe that'll be a different video. So if I run that, we'll just see that it runs. And yep, it runs with no errors, it saves the data. And that would be how you do acquisition. So, and then you would need to open up lies or something else to access that HDF5 file where the data is stored and see the data if you wanted to do that. Okay, so I think I'll stop there. This is just a basic tutorial on how to use a PulseBlaster and an NI DAQ card with Labscript. Thank you for watching.